linear transformation. Alright, before I introduce linear transformation, I would like to review basic concepts about functions. Alright, so let A and B equal sets. That's arbitrary sets. So a function f from A to set B. The notation will be f A to B. Right? So a function is a rule to assign an element y in B, and y in B to each element x in A. Okay, and the notation is denoted as f of x equal to 1. Okay, so it's a rule. So now for each element in A, we assign an element y in B to x. Okay, and this is the notation. And in this case, y is called the value of function f x. All right. So let me take an example. All right. So let's A is a set consists of alphabets A, B, C, D, and B is a set consists of 1, 2, 3, 4, 4 numbers. Okay, and so the first example, a function, and for each of the elements in A, all right, so for each of them, say A, B, C, D, so we have to assign an element B, right, to, for example, A, so we have to write here, right, so we have to fill up the value. So the value of f at A is, well, just up to you. So for example here, I will say 1. So 1 is the value of f at A. Okay. And the value of f at B, again, we assign 1. Okay. And for C, I will assign say 3. Right, so you can see that we have a lot of choices. Okay. Okay. Maybe it's windy, and I have to turn, thank you, the air condition on. First, the single, this one. Thank you. Yep. Okay, so this is one possible assignment. All right, the second example, say G, another function from A to B. So the assignment Okay, so it's up to you. For example, it's 4, 2, and 3, 1. Right. So from this example, we have an observation. Okay. So if the size of A, so the absolute value is just a symbol to denote the size of A, means the number of elements in set A. So how many elements do we have in set A? 1, 2, 3, 4, right? So we have 4 elements. And in general, suppose we have n elements. And similarly, the size of B is m. So the question is, okay, how many functions, right, from A to B can we have? So we may ask this particular question. Well, as here, we have by the definition of function that for this example, each of the elements in A, say either A into B is the same as C, we have to assign an element in B to it, right? So for this choice, as I just said 1, but you can see that for A, you can select one of the 4, right, elements. So you have 4 possibilities here. And for little b, you have, again, 4 possibilities to assign here. And the assignment will be independent of the assignment for little a. So you have 4 possible ways, you have 4 possible ways, you have 4 possible ways, you have 4 possible ways. So by the multiplication principle in combinatorics, you know that the possible number of functions you can build will be 4 times 4 times 4 times. In general, here, for each element, okay, you have the assignment will be, you have m possibilities. And then for the next element in capital A, you have again m possibilities. So, right? So you have n. Right? So you have n. And so that would be m to the nth power. So in general, you have not many functions. Any questions? Okay, so in the previous example, A equal to B equal to 4, they are 4 to the 4th power, so that would be 256 functions. From A to B. Okay. Now, we go back to the definition of function. A, alright, will be called the domain of the function. and B is called the codomain of f. Okay, so A is called domain of function f, and the B is called codomain of the function. Now the range usually use notation f of A of the function f is the set consisting, right, of all possible values of f, i.e. F of A is the y consists of all y and b such that y is equal to f of x, and for x in A. For example, in here, the f of A, right, consists of possible values. So 1 and 3 and 4 are possible values. And here 2 hasn't been assigned, right, for any element in set A. So FA will be 1 and 3 and 4. And of course, the range must be a subset of the codomain. And for G, the G function, 1, 2, 3, 4, that is equal to 2. Okay, and so from here we know that this will be a subset of the codomain. Okay, that. Any questions up here? Just a review, right? So I think that you all know this concept about functions. Okay, now for set A and B, as for here, we know we have 256 functions from A to B. Among these 256 functions, some of them have special properties, and we want to point out those special properties. So now a function from A to B is called 1 to 1, or sometimes called injective, right? 1 to 1 or injective. If f of x is equal to f of x prime, then x must be equal to x prime. I.e., another way to say that, if x not equal to x prime, then their value should be distinct. So in our logical argument, say here, so this is P imply Q. Okay? So if P implies Q, right? If this is true, then function f is called 1 to 1 or injective. So another way to say is that, not. So here is negative Q, prime negative P. Okay. This is about one-to-one functions. Another kind of function, a function f from A to B is called onto or surjective. Right, surjective. If the range of f is equal to the codomain. Okay. Third one, a function f from A to B is called one-to-one and onto, or called bijective. If f is both one-to-one and negative and onto. Okay, so let's see this function. For this function, is it one-to-one? No, 1. Because when A not equal to B, but the value they're equal. So value is this statement. Right, so f is not 1-to-1. Okay, from here. Is f onto, look at the range. We see that the range here not equal to, so it's included but not equal to 3, right? So f is not onto. So how about G here? Okay, you see that if we have different elements corresponding to different values, right? So you see that G is 1-to-1. How about is G onto? Well, you see, yeah, because the range is equal to the codomain. So G is onto. So G is bijective. Question? It is quite often we have the following situation. Let f is a function from A to B, and g is another function from B to C. Okay? So the codomain of f becomes to the domain of C. The composition, or called the composite, denoted as G and circle F of F and G is defined as a function from A to C. Alright, so G circle F becomes a function. Okay. By the following way that okay. Now the value of G circle F at X will become to G of F of X. That's the definition for all X A. Alright, so in a diagram, often in many situations, we will use this diagram. And the first function is from A to B called F, and this is G. And so an element X here then goes to B with the value F of X. And then this F of X will go to C under G. Okay. This is another way to describe the composition of two functions. Okay, so example. Right, so F A is equal to A, B to B, C equal to 1, 2, 3, 4, and C is equal to star, and the percentage sign up, and F from A to B as in the previous example. Here, previous example here. Okay. And H is from B to C by the following assignment. So I will specify 1 will go to H of 1, H of 2, H of 3, H of 4. Okay, so 1 will go to percentage sign, star, and the percentage sign. Okay, so now H of F as defined as A to C. So now we want to know what is the rule for this composite function. The H of X, A. Okay, so by definition this is H of F of A. But F of A is 1, so we have H1, and H1 is here is the percent sign. Alright, so A, the value, so the value of the function at a equal to the percentage sign. B again, because f b is 1, so again this is the percentage sign, and h of f, c, and f of c is 3, and h3 is star, simple, okay. H of f, b, h of d, which is h of 4, so that would be the percentage sign. All right. Okay, so from definition now, the composite of two functions is well defined, right? Because we know the rule, we know the function f and function g. Okay. Now, given a set A, the function called ID sub A is a very special function from A to itself. Okay, so A to A defined by the identity A. So the rule is that the assignment for an element x in A is itself. Okay. All right, so this function is called the identity function. So the identity function on A. Okay. The identity function is a very special type of function. Okay. It just assign to each element x in A, the value is just itself. So this is called identity function. And from the definition, you see that it's one-to-one, right? Because and onto. So the identity function on A is bijective. Okay, so it must be one-to-one and onto. So it is bijective. X, a function f from A to B is called invertible if there exists, right, a function h from B to A such that, so f is a function from A to B. Now, if there exists a function from B to A, so the codomain of f comes to the domain of h. Okay? The contrary, the domain of F becomes to the codomain of H, such that the composition H of F O F is the identity function of A, and F combined with H is the identity function of B. Okay. So that is A goes to B, goes to A. This is F, this is H, and the X. So you must have this phenomenon, F of X. Okay? So X map to F of X, and then here we have H of F of X must be equal to X if this is true. Okay? And from B to A, this is H, then goes to B, X, F. So for Y, it goes to H of Y, and then goes to F of H of Y, which is equal to 1. Okay? So to check a function F is invertible, first of all, you have to guess or pick up a function H from B to A. You pick up. So you should find some way to get a candidate. And then you have to check two things. First thing is that this composition comes to an identity mapping of A, and this composition comes to an identity mapping of B. Usually, the first step is part is one, pick up a candidate. Of course, you can guess quite a few candidates, right? And if you get a value, then you should try again. After you try many values, then you may think about that. Well, this function may not be invertible, and then you have to prove that. Okay, you have to prove that. So anyway, so this is the definition. You can see. Okay. Excuse me. Now, in this case, okay, means that if F is invertible, and we can find the function H, right? In this case, H is called an inverse function of F. Okay? So it means that we can find an inverse. So let's see. We look at this example. Is the function F here invertible? Well, the flow in this function is that when we want to go back, right? But because the mapping F, the function F, right? Does not get to us value, right? You can see. So we won't have problem because if we want to define a function h from B to A, how about the assignment of the h function at 2? That would be a question. But for this one, it seems that to go back, because A equal to 4, right? B equal to 2, C equal to 3, D equal to 1. So it's 1 to 1 and onto. And so that we can say create a function so that 1 will map to B, 2 will map to B, 3 will map to C, and 4 will map to A. And then we can find that would be a good candidate. So, so maybe for this function, okay, so for this G, a possible candidate, all right, of an inverse function h of G is equal, and you can specify okay, so h1 we would like to, so we want to go back, right? So h1 goes to D, 2 goes to B, 3 goes to C, and 4 goes to A. Right? So now we have a candidate. So we create, this is indeed a function because we assign a value to each of the elements in C. This is a candidate. And then you will verify these two things. Okay? You verify that. Okay. So I ask you to verify, and the answer will be yes. Okay? With this H, then the composition of H and G and the composition of G and H will give you identity functions. Okay. All right, so I will not do the whole thing, but I ask you to check at home. Okay. And so please check that. H is indeed inverse function of G, right? So we find that. And at this moment, you will say, could we find other inverse function for G? And we find out. Right. And so we might have that question. So the next lemma lemma 2.3.8 state that if H and H prime are inverse functions of F A to B, then we must have H equal to H prime. So this lemma tells us that inverse function must be unique if it exists. Okay? So, so we have to provide a proof of that. Okay, I'll proof like here. Now, for h, we have, because h is an inverse of f, so we know h of f is the identity matrix of A, and the f of h is the identity matrix of B. And for h prime, we also have the same property. H prime, circle f is the identity function of A, and the f circle h prime is the identity function of C. Okay, so this is a given because we said f h and h prime are inverse functions of f. To show that these two functions are equal, right? It means that h of y equal to h of prime y for all y in B. Okay? So we have to show that. So now for any y in B, we start with h of y. Okay, h of y. And h of identity, okay, because identity function map y to y itself. So no problem, right? You have that. And this one is h. Alright, so this identity of y. Okay. So the composition of h and the identity function is equal to h. Yeah. Now you have h, and the identity function of B, we can say this one or this one. But because we want to reach this result, this is our destination. So you should pick up this one, right? So it will be f circle h prime y. Okay, now the composition actually, you can do the composition for the last two, right? And then you do the composition. Or you can do the composition of h and f first, and then prime. Okay. So I implicitly use a property about composition. The composition is associative, means that the order of composition is not important. It doesn't matter. Okay, so that you can do these two first, and then do a composition for this one, or you can do this first. Now, if we do this one, h of f here is the identity function of A. So this is identity function of A. Okay. And what is that? So this is identity function of A, h prime, y. Okay? But identity function give you the h from y already. So we have done. Because from hy, we reach to h from y. So they are equal. Questions? Okay, so the conclusion is that an invertible function f from a to b has a unique inverse function. And this unique inverse function will be denoted as f minus 1. Okay, so we will give a particular name for the unique inverse function for f minus 1 from b to h. Alright, so now we are about the time to prove the following theorem. To give you a necessary and a sufficient condition that a function is invertible. So a function is invertible because we get some hints from this example. This example, she tells that it is one-to-one and onto, and we find that we are able, it's easy to construct a candidate of an inverse function like this one and check it. Okay, so now a function is invertible if and only if f is bijective. Means that if and only if f is one-to-one and onto. Alright, so I'll provide the proof here. First of all, the forward direction. So assume that f is invertible. Okay? Alright, for x prime in A such that f of x equal to x prime. Okay, so the situation is that suppose we have two elements in A such that they have the same function value. Now, because f is invertible, so it's inverse. Alright, because this function value are equal, right? So when we take the inverse function on these two values, they should be equal. But this is sorry. Right. Okay. And this is identity function on A, and this identity function. So x should be equal to x. So we start with the equality of function value. We end up with the equality of these two elements. So the conclusion is that f is 1 to 1. Okay? So we get to this conclusion by using the inverse function of it, because we know f is invertible. So we get to that. Now for y in B. Now y is actually by using the identity function of B, you get that. Alright, and the identity function is the composition of f and the f inverse. Okay? Because the f, this is the inverse, so f circle f minus 1 is equal to the identity function. So we have that. And then, so y is actually f of something. Okay? So y is a function value of an element in A. Okay, so let x to be f inverse y, which is in A, of course, right? Because the codomain of the f inverse is A, so that there. So now y is equal to f of x for some x in A. Okay? So that means that y is in the range of A. Now, so for any element in B, the conclusion is y should be f of A, so that B is a subset of A. Okay? So this will prove that. Because the element in B is an element in the range, so B should be a subset of A. But as we know, range is always a subset of B. So the conclusion is f of A is equal to B, i.e. f is onto. Okay, so we established that f is onto 1 and f is onto. Now, of course, that then the function f should be like this. Okay, so we use the property given that f is invertible, then we prove that f is bijective. Any questions about the proof? This is the first half of the proof. Now, if there's no problem, now see the converse part. So assume F is bijective. Okay. So now we construct a candidate. Okay, H from B to A. Right, so we want to construct a candidate. Right, in the following way. All right, so now for a Y in B, all right, there is an X, right, in A, such that f of X equals to 1. Since F is surjective. Because if F is surjective, then the codomain is equal to the range of F. That means that each element in B should be the value of the function F at some element A. So that if we pick up such, so there exists, means there should be at least one. Like, okay? Such as this is because this is subjective. Right? So we find an X. And such that this is true. Now, if there exists an X prime in A such that Fx prime is in Y. So, because we are wondering if there are other elements in A with the same value. Okay? So suppose we have this situation. So if there is an X prime in A such that the value of Fx X prime is the same as the value of F at X, which is equal to Y. Then X prime must be equal to X. Since F is 1 to 1. Okay? So the assignment will be unique. So the selection alright, so this unique. So this unique X will be assigned as the value of H at Y. Okay? Remember, we want to construct a candidate, right? So we want to construct a function X. So for every element Y in B, we should assign a value for it. But how to do that? Okay. So the following argument is the way to do it. So first of all, from F, we know that there must have at least one X in A, right? Such that the value of F at X is equal to 1. So we know there is one X with this identity. And the next question is that can we find another X prime have this identity? And the answer is no. Only one. Because F is 1 to 1. Alright? So we have a unique X And this unique x will be assigned to that, such that f of x equals to 1. Okay? So there is only one x such that f of x equals to 1. This is very important. Okay? Alright, so now we check, because we now already construct h function, right? We already construct that. So we have to check two things, right? First of all, the composition on x, right? We check. This one must be the identity function on A, right? So we have to see that. Okay, and this is f of x, right? And this one is 1. But because that for this one, our assignment, right, should be x by our rule. So here is by the construction of h. Here. So that h is equal to identity of a. Alright, the other check. So for B, by the assignment, this is x. Okay? And this is y, right? Okay. So that f of x so the conclusion is that h is an inverse. Okay, and we have that. Questions? Right. Right. So so up to now we introduced review the basic concept about function, invertible function, composition of functions. Okay. Now we are going to our main theme. Of course, they are infinitely many. Kinds of functions, okay, from Rn to Rm. For example, you may have x1, x2 up to xn. You go to x1 square, x2 square, xn square, maybe something like x1 multiply x2, multiply xn. You may have a lot of maybe another function you can define. Okay. So, but in linear algebra, we are most interested in the following kind of functions. Right. So for linear algebra, we will define special kind of functions from Rn to Rm. So a function t from Rn to Rm is called a linear transformation from Rn to Rm if the following properties are satisfied. This property for all x, y in Rn and alpha, beta in R. Yeah, okay. Just one review. I've write it together. Okay. So so verbally, this identity tells that for this linear combination of x and y, so this is just arbitrary linear combination of two elements, two vectors in Rn, right? Then the value of this linear combination, okay, after the function, the actual function t, becomes to a linear combination with the same coefficient. So the form is the same. But the vector now should be in Rm, right? Because of the function making. So that it will be the t, the value of x, vector x in Rm, and the value of y in Rm. So they are vectors in Rm. Okay, and you can see that they just keep the same formulation of linear combination. Right. So any function has this property will be called a linear transformation, okay, from Rn to Rm. So that would be special, right? Because it should have this property. So let me take an example. T from Rn, say 3 to 2, okay, and making is x1, x2, for this one, alright, so we should verify whether this function is a linear transformation or not. Okay. So now we will transform alpha plus beta okay, so that would be alpha x1 plus beta y1, alpha x2 plus beta y2, alpha x3 plus beta y3. Alright, now we apply the rule here. So this comes to alpha x1 plus beta y1 square plus alpha x2 plus beta y2 square and x3 here. So that this is alpha x3 plus beta y3. And it is apparently not equal to alpha right, which is alpha x1 square x2 square x3 plus beta y1 square plus y2 square y3. So this is alpha p of x1 x2 x3 plus beta p of y1 y2 y3. So the purpose is to verify whether the value of this linear combination becomes to this linear combination. Right. So we go back. By definition of T, it is this vector. Okay, and for y1, y2, y3, the value after the action of T would be y1, which is this vector. So the combination together is this one. And the problem is here. Apparently, this one is not equal to this one. Right? Apparently. Because that you see that this is alpha square x1 square plus 2 alpha beta x1 y1 plus beta square y1 square. Okay? And the plus alpha x2 square to alpha beta x2 y2 plus beta square y2 square. So this sum, this expression is apparently not equal to this expression. So that they are not equal. So the conclusion is that P is not a linear transformation from R3 to R2. Okay. All right. So you can take many examples that they are not linear transformations. But on Friday, I will characterize those functions to be linear transformations, okay, by giving a theorem. So that I stop here and take a short break.